Hey guys, welcome back. We'll do the gas laws calculation now. Now for these problems, hopefully you have already tried them, all right? If you haven't tried them, maybe you can watch one or two and then try them, all right? I want you to try them and then come back and check, all right? That's the goal here, all right? So these gas law calculations, we have two formulas, all right? I have P1 V1 over T1 equals P2 V2 over T2, and we have PV equals nRT. Those are our two formulas for gas laws, right? The combined gas law and the ideal gas law. All right, so let's dive into number one. We have 2 liters of an ideal gas is heated from 50 degrees Celsius to 150 degrees Celsius under a constant pressure of 1.0 atmospheres, right? The question is, what happens to the volume? All right, so is this a combined or an ideal? Well, I have constant pressure, so the pressure is not changing. And it's an ideal gas, right? And we're not adding any gas, we're not taking any gas away. So the moles are constant. So I'm thinking we're going to have a P1 V1 over T1 equals a P2 V2 over T2. And on the side, if you want, P1 V1 T1 P2 V2 and T2. So now we know that constant pressure, 1.0 atmospheres. 1.0 atmospheres. So if P1 equals P2, I can just cancel it from my equation. How nice is that? V1 is 2 liters. We don't know V2, that's the question mark. And T, I got from 50 degrees Celsius to 150 degrees Celsius. All right, let's just dive in. So we're going to have V1 over T1 equals V2 over T2. And I'm solving for V2. So I'm going to multiply both sides by T2. All right, so that means I get T2 times V1 all over T1 equals V2. So that means V2 will equal, I'm going to have T2 150, V1 is 2.0 liters, and V1 is 50 degrees Celsius. All right. And so that looks like that would be 6 liters. And usually, every time I do this in class, sometimes a student raise their hand, and they should, because hopefully you notice that there's an error here, right? What's the problem? Temperature's on the bottom, right? So this needs to be in Kelvin. Temperature needs to be in Kelvin. How do I get to Kelvin? We have to add 273 to both of these. All right? So that means we actually have 323 Kelvin here and 423 Kelvin. So that's not 150, all right? This is 423 Kelvin and 323 Kelvin. So it's not 6 liters, right? My actual temperature or volume is 2.6 liters, which is a much better answer, all right? So make sure we convert to Kelvin for these. That's very important, very important. All right, now, number 2 continues with number 1. To what must the pressure be increased? Was the question. At 150 degrees Celsius to reduce the volume back to its original value of 2 liters. Same thing now. We have P1, V1, T1, P2, V2, T2. temperature is 150 or 423 Kelvin, and it's the same for both. So temperature is constant. Pressure. P1 was 1.0 atmosphere. I don't know P2. V1 is 2.36 liters, right? 2.6 liters to 2.0 liters. All right, so we're going to have P1 V1 equals P2 V2. Do I need to worry about T? I don't think so. I'm going to write it down. T1 and T2, and we can cancel it, all right? So we don't really need to. And I'm solving for P2, right? And so that means P1 V1 equals P2 V2, or P1 V1 all over V2 equals P2. So that means P1 is 1.0 atmospheres. V1, 2.6 liters, all over 2.0 liters. And so it looks like for the pressure, I'm going to get 1.3 atmospheres. So there we go. Next one, number 3. Sulfur dioxide, which is a gas. Oh no, I'm sorry, I have a different one. Under constant pressure conditions, a sample of hydrogen gas initially is 88 and 9.6 liter is cooled to its final volume of 3.4 liters. What's its final temperature? All right, what do we got here? We have, let's see, I got temperature, I got a volume, I got another volume. Temperature, no change. So I'm guessing, I'm not guessing, but I'm guessing this is P1 V1 over T1 equals P2 V2 over T2. So we got P1 V1 T1 P2 V2 T2. All right, so what do we have here? Under constant pressure conditions. All right, so that means P1 and P2 are the same. We don't need to worry about them. They are the same. So I'm just going to put a line for both of them. And we're going to just do that. And we're going to do P is gone. Sample hydrogen gas at 88 degrees Celsius. So it's 88 degrees Celsius, right? And can we keep it in Celsius? No, I have to do 88 plus 273 to give us 361 Kelvin. All right, 9.6 liters is cooled. It's cooled until its final volume is 3.4 liters. So we have our temperature here and our two volumes, 9.6 liters and 3.4 liters. The question is, what is the final temperature? T2. How do we solve for T2? So we have V1 over T1 equals V2 over T2. I think I'm going to cross multiply. So then I would have V1 T2 equals V2 T1. And then divide by V1. So T2 is equal to V2 T1 all over V1. Let's see how we do. All right, because what did I do here? I took this, I times both sides by T2. And then here I divided by V1. All right, so V2 is 3.4 liters. T1 is 361 Kelvin. And V1 is 9.6 liters. And so if we do that, you take your 3.4 times your 361 divided by 9.6. I got 128. Actually, I got 130. So I actually get 127.85 Kelvin, which is 130 Kelvin. All right. And so that's it. It doesn't say. Now, technically that's negative 100 and let's go with 50 degrees Celsius. It's negative 145, but let's go with 150. But we don't need that. Really, 130 Kelvin is all we needed. All right. Next one. Sample gas at 15 degrees Celsius. So 15 degrees Celsius right away. Hopefully now we're realizing we're going to add 273 to our Celsius, right, to get 288 Kelvin. Right? It has a volume of 2.58 liters. What will the temperature be if this gas occupies 3.25 liters at a pressure of 1 atmosphere? Another one. So I'm thinking this is also a P1 V1 over T1, P2 V2 over T2. All right, so now P1. I think it's 1 atmosphere, right? I don't know if you guys see that or not, because we're looking for a temperature. And we got 1 atmosphere. We have another temperature here. We have a volume. And another volume. And a temperature, or pressure. So pressure is 1 atmosphere. Volume, temperature, pressure, volume, temperature. So V1, 2.58 liters. T1, 288. P2 is still 1 atmosphere. V2 is 3.25 liters. And T2 is our question mark. All right. Well, we can cancel out P right away because it's the same. All right. And we're solving for T2 just like we did above. Right? And so we know T2 is equal to same derivation. Well, let's just do it. Let's just do it all. So cross multiply. But before I do that, I'll rewrite. To get V1 all over T1 equals V2 all over T2. Multiply both sides by T2. So we get T2 V1 equals V2 T1. And then we divide both sides by V1. So T2 equals V2 T1 all over V1. All right, so now we have V2, 3.25 liters. Temperature, 288. New volume, or the original volume, 2.58 liters. And so we'll take our 288, or 3.25 times our 288 divided by our 2.58. And you should get 363. And it doesn't say temperature, but that's 89. That's actually 90 degrees Celsius. Hopefully that works. All right, let's continue. Suppose we have a 12.2 liter sample, right, at half a mole oxygen gas, pressure 1 atmosphere. Great. And temperature 25 degrees Celsius. All of the oxygen were converted to ozone, O3, at the same temperature and pressure. What would the volume of the ozone be? Whoa. Okay. So we have what here? I have oxygen gas, O2. O2, and that's going to O3. Well, let's see. I would need to put a 3 here and a 2 there. That's, what do we have? We have 12.2 liters, 25 degrees Celsius, which is 298 K. Half a mole. One atmosphere. All that is going over to O3. So I'm going to take my moles, 0.50 moles O2. And we know it's what? 3 mole, didn't change color. 3 mole of O2 to 2 moles of O3. 0.3, repeating, moles of O3. So that's how much O3 now I have. And now we want to know what the volume is. All right, so my moles change, so that's a PV equals nRT. And I'm looking for the volume of the ozone. I'm looking for V here. So V equals nRT over P. So let's do this. N would be 0.3 moles, repeating, but just 0.3 because I actually have 3. I have 2 sig figs. All right, I have 2 sig figs, yes, 3. Fix that for us. All right, so now R, 0.08206 liters, atmospheres, moles, and Kelvin. Our temperature was 298 Kelvin, and our pressure was 1 atmosphere. So that means our volume, if you do this math, 0.33, 0.33, times R, 0.08206, times your 298, divided by 1, which is it. I got 8.07, which means I get 8.1 liters. All right. How about that? Number 6. Oh, density of methane. That's the density one. Oh, I think the answer is right there at 0.65. Let's see if that's the answer. So the density of gas, if you remember, density equals pressure times the molar mass divided by R and T. So the density would equal the pressure. Looks like the pressure is 1 atmosphere. Molar mass of methane, CH4, right? So the molar mass, carbon is 12.01 plus 4 times 1.01, which is, looks like it's 16.05. So 16.05 grams per mole. R, of course, is R, 0.08206 liters, atmospheres, moles, Kelvin. And temperature, 27. So you add plus 273. And I wrote over that, but that's 300 K. So if I take my 1 times my 16.05 divided by R, which is 0.08206, and divided by our 300, we get 0.65. How about that? And grams per liter is the right unit, right? Because let's see what cancels here. Atmospheres is gone. Moles is gone. Kelvin's gone. And it's grams per liter. That's perfect. All right. Number 7. Moving right along. Pressure of a 340-liter tank that contains 5.67 kilograms of helium at 25. All right. Well, since I don't have initial and finals, I'm assuming this is going to be a P, V, N, R, T. I have a V, 304.0 liters, right? That's my volume. We're looking for the pressure. I have 5.670 kilograms. That's not what I want. R is, of course, always 0.08206 liters, atmospheres, moles, Kelvin. And temperature 25, which is 298. Well, it looks like we have to do some math. So I have 5.670 times 10 to the third grams of helium, right? Because that's kilograms. Kilo is 10 to the third, right? And we know that 4.00 grams of helium is 1 mole of helium. So if I do my 5,670 grams divided by 4, I get let's see, what do I get? 5,670 divided by 4. I get 1417.5 moles of helium, which to 3 figs is 1420 moles of helium. All right, so now we can plug in our PV equals nRT formula. We're looking for the pressure. The volume is 304.0 liters. N is, actually I have 4 sig figs there, don't we? I almost made a mistake on you guys. This should be just an 8. This is 1, 8. 1418 moles of helium. R, 0.08206 liters, atmospheres, moles, Kelvin, and 298 Kelvin. So that means the pressure, we are 1418 moles times R times your 298 divided by your 304. All right, I get 114.06. Now, I have 4 sig figs, right? And so that means we get 114.1 atmospheres. Now, the only caveat to my sig figs is right here, right? I only use 4. I only use 3 sig figs here instead of 4. Because technically that should have been 5, 7, or 5, 6, 7, 4.002. And I actually only have 1417. So technically speaking, that should be a 7. If I use 4.002 grams. And does that change anything in our overall answer? I don't know. I doubt it. 114.0. So it should be 114.0. If I was doing 4 sig figs appropriately with the molar mass. All right, next one, 8. What temperature in degrees Celsius is 121 milliliters of carbon dioxide at 27 degrees Celsius at 1.05 atmosphere occupy a volume of 293 milliliters at a pressure of 1.4 molar? Well, looks like we have the combined gas law here. So temperatures, I have question and temperature, and let's see, I have volume. Oh, there's my other temperature, 27. And another volume. And pressure. All right. So this, I would think, would be a B1, B1, T1, P2, B2, T2. All right, what do we have? Pressures. P1 was 1.05 atmosphere. P2 is 1.4. V1, 121 milliliters. V2 is 293. T1, 27, which is plus 273, so that's 300. Okay. And I don't know. All right. So, P1 V1 over T1 equals P2 V2 over T2. Of course, we're solving for T2. That's what we don't know. So, I need to figure out, I need to get T2 out of the bottom. The best way to do that, I know, for most of us, is to cross multiply. T2 times P1 V1 equals P2 V2 T1. And then we're going to divide by P1 V1, so T2 would equal P2 V2 T1 divided by our P1 V1. All right, so T2 is going to be P2. P2 is 1.40 atmospheres. V2, 293 milliliters. T1, 300 Kelvin. P1, 1.05. And V1 is 121 milliliters. All right. And so I take my 1.4 times 293 times their 300 divided by 1.05, and we're divided by 121. I get 968.595. And some change. And let's see, how many sig figs do we have in this time? Well, 300 now is 3, right? Because I'm adding. So 3, 3, 3, 3, 3, 3. I had 3. So 969 Kelvin. All right, so 969 Kelvin, which is temperature we want in Celsius, don't we? So that means we have to subtract, and I get 696 degrees Celsius. Fantastic. All right. A sample oxygen has a volume of 2.5 liters at STP. How many grams are present? Ooh, this is different. So I have a volume, and I have a temperature, and I have a pressure. All right? And so if I do a P, V, N, R, T, I don't know N, but I'll have to make that in grams. I know a P. P is 1 atmosphere. Standard pressure. V is 2.50 liters. R, of course, is R. And T, 0 degrees Celsius or 273 Kelvin. All right, so let's do this. PV equals nRT. So I'm going to do 1 atmosphere. We have 2.50 liters equals, we don't know the number of moles. We know R, 0.08206 liters, atmospheres, moles, and Kelvin. And we know T at 273 Kelvin. So I'm going to pause right there. You notice I put the numbers in first. If that's how you like to do the problems, you are welcome to do the problems this way. I like rearranging it. All right. I'll be honest with you. I would have had these numbers over here and divided, but we're not doing that yet. Okay. And so I do the math. N would equal what here? I think we do the math, I get what? 0.111595. And I have, sig figs. Well, how many sig figs is STP? That's a great question, isn't it? And then this textbook, I don't know. We'd have to look. So right now, I'm just going to assume 3 sig figs. Okay? So 0.112 moles O2. And of course, we want to convert that 1 mole of O2, and we got to convert to grams. 32.00 grams of O2. And if I do that, I get 3.584, right? 0.112 times 32. I get 3.584 grams, and I get 3 sig figs, let's call it, so 3.58 grams O2. So that's what I get doing that. All right. Last one. An automobile tire, 23 degrees Celsius. All right, so hopefully now we see 23 degrees Celsius, and we add 273 to that, and we get 296 Kelvin. Hopefully we recognize that. It has internal volume of 25 liters, filled with air, total pressure of 3.18. Determine number of moles of air in the tire. Okay. So we are going to do, I have a pressure there. Determine the number of moles of air in the tire is my question. I have a volume. And I have a temperature. I think this is a PVNRT. All right. 3.18 atmospheres is our pressure. 25 liters is our volume. We don't know the moles we're solving for. We know R, and temperature is 296 K. So this one, PV equals nRT. Again, we are solving for N. So that means PV over RT is N. So N would be P, 3.18 atmospheres. V, 25.0 liters. R, 0.08206 liters, atmospheres, moles, Kelvin, and temperature is 296 Kelvin. So that means the number of moles, if I do this, 3.18 times your 25 divided by R, divided by our 296, I get 3.27298. And I have 3 sig fig, 3, 3, 3. We're going to do 3, so N equals 3.27 moles of air. All right, so that was a bunch of gas laws problems. I hope that makes sense to you guys. If you have any questions, reach out. Otherwise, we'll see you next time. Take care, guys. Bye.